we'll finish up our talk about the uncertainty principle by expanding out to 3 dimensions here. So we already talked about just 1 dimension with our uncertainty and momentum multiplied by our uncertainty and position being greater than or equal to h bar over 2. We can expand that out to all 3 dimensions with just our Cartesian coordinates, again, y and z here. And we can say that all of these different dimensions are independent from each other. So that uncertainty in momentum and position in 1 dimension is completely independent from the uncertainty in a different direction. That's pretty much all we need for now with our uncertainty principle. So the other thing in this section would be expanding this out to a different type of uncertainty, energy and time. So this is slightly different than what we've been doing. So the momentum position uncertainty that we see up here kind of tells us that the width that we take up in space, or that we feel pretty certain that our particle is at in space, is inversely proportional to, we'll say the width, even though it's not exactly a width, in spatial frequency. Right? Remember, we can relate momentum to, oops, I don't want to write it quite like that. We can relate momentum to that wave number or to our wavelength. And so there's a variety of k values that'll give us kind of a more certain width in space in x, y, or z, right? So energy time uncertainty is how we're going to relate kind of a width in time, so a certain time interval, to a temporal frequency. So in other words, we're going to be able to write this. And the derivation is pretty similar. Again, we're going to relate that angular frequency to a period of motion, and our energy is related to that angular frequency. So the where in time and the energy is going to be inversely related, our certainty of those 2 things. Another way to say that would be that if a state or a particle exists for a limited amount of time, that's our delta t, its energy is going to be uncertain. That's our delta E. So a state of motion or state of being a not stationary state exists for a limited amount of time, its energy is uncertain. So in the next section, we kind of apply the uncertainty principle and talk about what's called the Copenhagen interpretation of quantum physics. So what we're doing here is we're carrying out an experiment on a particle. So we'll call it experiment A. And we're going to apply external forces in such a way as to determine both its position and its momentum as precisely as possible. So when we say as precisely as possible, we're saying we're going to do this kind of thing, right? So we're going to make that greater than or equal to and equal to with our uncertainty. So when we apply this, that means we're going to force an electron beam, say, through a narrow gap. So in their example, they say, let's pretend delta x is 100 micrometers. And we're going to get a wave function from that we'll call psi of A. So we're calling this experiment A, and we're going to get a wave function psi of A. So if we found the wave function, we haven't exactly found the particle, right? We found a probability amplitude. So they say our other experiment is experiment B, where we put a detector. So here's our detector screen. This is our experiment B. And each of these particles hits the screen. So each of these hits is an experiment B that we repeat over and over. We have the same electron beam. As far as we know, they're identical particles. We put them through here where we have a certain limited uncertainty in position, and we get the particle at different locations every time a single particle hits the screen. So the first experiment A gives delta X and gives a probability amplitude. That's this guy. The experiments B changes the wave function each time we detect a particle. So we have repetition with what we see as identical particles, but we get, with this over and over repetition, a distribution of particles that match our probability distribution. So this leads us to the Copenhagen interpretation. Let me see if I can write this. That should be a capital C. Which basically says that until an experiment actually localizes a particle, that particle simply does not have a location. So simply by detecting it, we have changed the wave function to localize it down to that certain spot. And this is kind of not intuitive. I know I keep saying that. But this is the widely accepted interpretation of quantum physics.